Hey guys, today we will go over lesson 3 of our physics class, and that will be projectile motion. So far, we have only been dealing with motion in one dimension, either in the x or y directions. But what would happen if instead of launching an object straight up like we did in free fall, we were to throw it at an angle theta? Well, the best way to learn this is by solving practice problems, so that's what we'll do. So here is the problem. An object is launched with an initial velocity of 38 meters per second at an angle of 67 degrees above the horizontal. How far from its original position does the object land? So I already drew here a little diagram to make things a little clearer. How far from its original position does the object land? So what the question is asking is what is this distance here, which is delta x. So I also made a little table here that will make things simpler because this angle makes everything complicated, right? We'll have to analyze the motion of this object in both the x and y components, and therefore we will write down our knowns and our unknowns in both of those components. So I already put a question mark here for delta x because that's what we're looking for. Delta y, we do not know delta y. And we're gonna fill this table as we go into the problem. Initial velocity. Do we know the initial velocity in the x and y components? Well, it is not given in the problem, but we can figure them out fairly easily. So in order to make this simpler, I will I drew a little triangle here to represent the initial velocities. This is 67 degrees. This is our initial velocity of 38 meters per second. And we have to find the x and y components of that initial velocity. So you can see here that this is a right triangle. And how do we relate the opposite side of a right triangle to its hypotenuse? Well, we use sine. So sine of 67, or sine of theta, which in this case is 67, is equal to VOY, or the opposite side, over the hypotenuse, which is 38. So we can rearrange this to say that VOY is equal to 38 times the sine of 67. So VOY is equal to 34.98 roughly meters per second. We can do the same thing for VOX. Let me just write this down here first. Right here. And also VOY, we just solve for it, so I'm going to put it in our table. 34.98 meters per second. So VOX is the same thing, but with cosine, which is equal to adjacent over hypotenuse. Cosine of 67 is equal to the adjacent side, VOX, over hypotenuse, which is 38. So VOX is equal to 38 times the cosine of 67, which will be equal to, put it into your calculator, and we'll get 14.85 roughly. Okay, so put that in our table. Okay, now for acceleration in the x and y components. So to do acceleration, picture this. Look at this point, and pretend that this point is the object that is being launched. The only thing acting on this object is gravity, correct? Because once I applied an initial velocity on this object, nobody's touching it anymore. The only thing acting on it is gravity. Therefore, if this is the object, the only force acting on it is pointing down, and that is the acceleration of gravity. So in the y direction, we know that the acceleration is negative 9.8 meters per second, or g, meters per second squared, actually. And there's nothing acting on it on the x components. So we can safely assume that the acceleration in the x direction is just 0. Now, velocity in the x direction. If there is no acceleration acting on it, say that since velocity is just equal to initial velocity plus at, if the acceleration is 0, this entire thing just cancels out. So the velocity of the final velocity in the x direction will actually be the same as its initial velocity. So I'll just put here also 14.85. And in the y, we do not know the final y velocity. And we can figure it out, but we're not going to do that now. And time, I did not put time in the table. I put it like below it because time is going to be the same for both variables. And we do not know time, so we'll leave it blank for now. But now, the important thing is that we have enough information to solve the problem. So I mentioned that time was equal for both of them. And essentially, I want to see how much time it takes for the the object, which might very well be a particle, to finish this entire motion, to then multiply by velocity to get, displacement. For that, we'll see how long it takes first for the displacement in the y direction to be 0. Why am I doing that? Well, we see here that the initial position here is the initial position right here. Let me do it with a blue to make it clear. This is the initial y. The object will go up all the way to here, but then it will go down again. In the y, if we're only looking at the y component, the object did this going up, and then it went down on the same path. So the y displacement is 0. So we're assuming delta y to be 0 in this case. We're gonna use the position function for y, via y multiplied by t minus 1/2 gt squared in order to solve for the total time, because when we solve for t, we'll get two answers because t is squared. So one of the answers when delta y is 0 will be here, and the other one will be here. So delta y is equal to VOY, which is we found out that is 34.98 multiplied by t minus 1/2 9.8 t squared. When you solve this, you're gonna get two answers for t. Oh, actually, this delta y here is 0 because we set it equal to 0 in here. So when we solve this, we'll get two answers for t. One of them will be that t is equal to 0. And we will not use that one because that is, again, the initial time. We're solving for t final, which is the second answer, which turns out to be 7.139 seconds. Now that we have time, we can plug that time into the delta x function in order to find displacement in the x direction. So delta x is equal to VOX plus 1/2 VOX t plus 1/2 AT squared. And when we plug in our knowns, delta x will be equal to 14.85 multiplied by time, which is 7.139. Let me actually write the time is equal to 7.139 in here. Okay, plus 1/2 0, because we determined that the acceleration in the x direction is always 0, multiplied by 7.139 squared. So since this is 0, we just cross that one out. So delta x would just be equal to 14.85 multiplied by 7.139. And when you plug that into your calculator, you're going to get that delta x will be equal to 105.99 meters. And that will be the answer to the problem. So, from this problem, we learned a couple new concepts. Number one is that in projectile motion, the acceleration in the x direction is always 0. That means that VO is always going to be equal to, Vx is always going to be equal to Vox. And also, I'm pretty sure you guys remember from free fall that if I launch an object for a certain point in time, an infinitely small period of time, the velocity will be 0. So the velocity at the y is 0 at the top. Therefore, at the top of projectile motion, in this point right here, velocity will be equal to Vox, or which will be equal to Vx at the top. And yes, and we relate the y and x components using Pythagorean theorem, which just says a squared plus b squared equals c squared. So that will be all for this video. Thank you guys for watching, and I hope to see you guys in the next lesson.